1.9, defining numbers. The natural numbers are numbers that you naturally count, 1, 2, 3, 4, 5. They are numbers that you count with your fingers. They're notated by the Gothic letter N. So not a regular N. What you do is you throw in another line and it makes it a Gothic letter N. The whole numbers are simply the natural numbers, and you throw in the whole, or the 0. It's notated by the Gothic letter W. The integers are the whole numbers plus the negative natural numbers. So now we have negative 1, 2, 3, 4, 5, and we have positive 1, 2, 3, 4, 5 along with the 0. This is notated by not just a letter Z, but has an extra line. The rational numbers. The rational number is a number that can be written as a fraction of two integers. So you're going to take an integer, which is the whole number or the negative numbers, and write a fraction with them. The answer to that is a rational number. It's not notated simply by Q, but we draw a Q and a line through it. If you were writing this on a computer, it would actually have like a shadow to it. The irrational numbers are numbers whose decimals don't repeat and never end. For these, we're pretty familiar with pi, 3.14, etc. E is another one we'll talk about eventually. These don't have a specific notation, but a lot of times we call them IR for irrational. The real numbers are all rational and irrational numbers. If it is not an imaginary number, it is a real number. This is notated by the Gothic symbol R. Now some more vocabulary. A set is a list of things in a group notated with braces, such as set A is equal to 1, 2, 3, etc. We could have simply said set A is natural numbers. Now it doesn't have to be numbers, but this is math class and that's why we use numbers. An example would be a set is a list of plants. So all plants could be a set. An element of the set is one of the things in the set. It's notated like this. X is an element of A. Where A is the set, up here we had the set, and X is the element. So we would say 1 would be an element of A. 2 would be an element of A. It kind of looks like an E, but it's actually more like a backward C with a line through it. A subset is another set, but where all of the elements are the elements of the original set. It's written again kind of like a backward C. So in our example above with the set A equaling 1, 2, 3 natural numbers, if I said B is a subset of A, then we could say B are simply the even natural numbers, or B are the odd natural numbers. They're a subset of the others. A proper subset is a set whose elements are all elements of another set, and the original set has more elements notated A, proper set B, where A is a proper subset of B. Basically, the subset means that you could actually have all of the natural numbers. It's basically repeating itself. We don't use subset very often or at all. We almost always use the proper subset. So for my example above with the even numbers, we'd be better off to write B is a proper subset of A when B are all the even natural numbers and A, like we said above, were all the natural numbers. Basically, for a proper subset, the original set has to have more elements or more pieces than the proper subset, whereas with a regular subset, they can actually have the same amount. The universal set is a set with all the elements from all the subsets notated by a special U. So a lot of times you'll see it written with two pieces, kind of like that. I'm no artist. Or if it's written on a computer, it basically has an extra line. One easy way of writing it would be simply to write a U with an extra line next to it. Now let's go through some examples to make this a little more clear. So up here we said that an example of a set would be a list of plants. So we're talking about all plants. If you can think of a plant, it's within that set. Now they want an example of an element of that set. Well, an example of an element would be my plumeria tree or a rose bush. So we'd say P is equal to a rose bush. And that would be one element of the set. P is equal to a rose bush. Are there other plants in the world? Of course. but that's just one element of the set. Now they want an example of a subset. Well, an example of a subset, think of another set of plants, such as trees. There are many different types of trees, but they are a subset of plants. Trees are a type of plant, and there are a whole bunch of types of trees. So an example of a subset would be trees. Because, yes, they are plants, and they have their own category. Next we ask, is this a proper subset? Well, are trees part of plants? Yes, we just said that. Do they have their own categories? Are there many different types of trees? Yes, there are. So is this a proper subset? Yes, because they are plants and they have their own categories. An example of an element of that subset would be my plumeria tree, would be my palm tree, would be an oak tree, any type of tree you can think of. Personally, I'm a fan of palm trees. Here's another example. The universal set A is given by 1, 2, 3, 4, 5, 6. Just those numbers, 1, 2, 3, 4, 5, 6. So an example of an element of that set would be 1, or 2, or 4, or 5, or any of those individual numbers in there. So the proper way of writing this would be saying 2 is an element of set A. We could have chosen any number we wanted. We say 2 is an element of A. An example of a subset would be, say, the even numbers, 2, 4, 6. So we would say B would be even numbers. Or we could write it another way, by actually listing out the specific numbers. Now we didn't have to choose even numbers, we could have said any of them. And we would say that B is a subset of A. Now, is this a proper subset? Yes, of course it is. Even numbers are their own set within the original set A. So we'd actually write it B. One more example, now using some of the vocab words that we've talked about. So they tell us that our set is the real numbers. So all real numbers. Basically any number. So they want an example of an element of that set. I could say 5, or I could say 7, or I could say 121. They're all real numbers, so they're all an element of the original set. Now give an example of a subset. Well, we could simply say the whole numbers. Are the whole numbers a subset of the real numbers? Yes. The whole numbers are 0, 1, 2, 3, 4, 5, etc. forever. Now, is this a proper subset? The question is, are whole numbers smaller than the real number set? Yes, they are. The whole numbers don't have any of the negatives. So we know that it's a smaller set. Whole numbers also don't have any irrational numbers because they're all going to be full numbers. So because the whole numbers is a set of its own, but smaller than the real numbers, then we'd say, yes, this is a proper subset. Now we're going to move on to proper notation. There's two different types of formats. The roster form of a set is what we talked about before, where we had a set and you list the specific numbers. So listing all of the elements, 1, 2, 3, 4, 5, 6. Set builder notation is a way of defining the properties that make the elements of the set. So we could say x such that x is a natural number, or x such that x is a natural number. The vertical line or the colon means such that, as in it is describing the x. So over here on A we have x such that x is an even natural number less than 10, less than or equal to 10, meaning 2, 4, 6, 8, 10. Versus in the letter B, they have the roster form, just 1, 3, 5, 7, 9. Roster, giving you the numbers. Think of the roster for your sports team. It lists out the players. Versus set builder just simply gives a description of the numbers. A union of two sets are the elements that belong to either of the sets notated by A, union B. It looks like a U but doesn't have a tail. Normally we write U's with a tail. This one simply is the U without the tail. An intersection of the two sets are the elements that belong to both of the sets, notated by A, that upside down U, B. You need to know the names. That's an intersection. So A intersection B. So a union is anything that is in either of the sets, whereas the intersection has to be in both. Now let's do a couple examples before we move on. Going back to the top, set A is X such that X is an even natural number. Remember, this is in set builder notation. If I want to change this to roster format, I could. I would say that A is equal to the set. We said the even natural numbers are 2, 4, 6, 8, and 10. Even natural numbers. So this is set builder notation, and this is roster format. Down here it says find U. That's known as the universal set. The universal set is everything in all of these. So we need to make a list of everything in all of these sets. Here I have the even numbers, 2, 4, 6, 8, 10. Here I have the odd numbers, 1, 3, 5, 7, 9. And in set C, we have X such that X is an integer from -3 all the way up to 8, not including 8. So if I was to write this out, my very first one says that was A. Letter B gives me 1, 3, 5, 7, 9. And then letter C, or set C, gives me the integers from -3 including to +8 not including. So we have, since 1, 2, 3, 4, 5, 6, 7 were already in the other sets, I don't have to rewrite them. So the universal set lists everything that I have from the top 3 sets. Now find A union B. Write the answer in roster form and set builder notation. So we're going to write the answer in 2 different ones. A union B. That means all the numbers in set A or in set B. So A union B is going to be the set of numbers 1, the set of all the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, because A included the evens and B included the odds. Now if I'm going to write it in the other notation, in the set builder notation, we'd say A union B is equal to, need a bracket, X such that X is a natural number and X is less than or equal to 10. Now, if you'd prefer to say X is less than 11, that's perfectly fine. I prefer X is less than or equal to 10. I like the equal sign better. If you're doing it on a computer where it's hard to get that equal sign, then you're probably just going to say less than 11. Next, find the intersection of B and C. That means it has to be both. So we're going to say B intersection C. B intersection C is equal to, now I need to go back up to B and see what's in both. B is 1, 3, 5, 7, 9. C is -3 to 8 in integers. It'll be a lot easier to actually write those out. So -3. So here I have letter C rewritten in roster form. Now I need to look to see where they're the same. I have a 1 here and I have a 1 there. Again with the 3 and the 3, the 5, the 7, and no 9. C is only less than 8. So the 8 shouldn't have been there because it's less than, not less than or equal to. Now I can take the numbers that are the same. Those are the intersection and write them down. If we're going to put it in roster form, we're going to write 1, 3, 5, 7. Now in set builder notation, we write B intersects C. Now you need to see what type of numbers those are. We look at them 1, 3, 5, 7. Well, they look like natural numbers to me because we naturally start counting at 1. But they're not all the natural numbers, they're simply the odd natural numbers. So that's what we say. We say B intersection C, bracket, X, such that X are the odd natural numbers. But they don't go on forever. They stop at 7. So we'll say also x is less than or equal to 7. Now if you just wanted to say less than 8, that's fine, but I like the equal sign. And close your brackets. Now some of you are going to be a little smarter and say, hey, I could have abbreviated the natural numbers. Yes, you totally could have abbreviated the natural numbers, but for our purposes, let's not confuse people and actually write the natural numbers. Going back to our vocabulary, we have the complement of a set, or the elements of the universal set that are not an element in a given subset. It's notated A with a superscript C or A superscript prime. If we take a look at our problem, we have find B prime, right in either form. That means I need to go back up to my universal set and cross out the numbers that are in set B. So set B was 1, 3, 5, 7, 9. So I take my universal set and I cross out the number 1, 3, 5, 7, 9. 1, 3, 5, 7, 9 were in B. I want the complement of B. That means I want all the numbers that were not in B. So I'm going to write it. B prime is equal to, and I'm going to list all the numbers that were not in B. Negative 3, negative 2, negative 1, 0, 2, 4, 6, 8, 10. This is going to be much easier to write in roster form. Moving on to some other vocabulary that you need to know. We have an upside down A, which means for all, a backward Z, which means there exist, the 3 dots in a triangle means therefore, and then we already said that the colon or the vertical line means such that. These are important things for you to understand and know. So for the examples we have, for all x greater than 1, and 2x is greater than x. So that's a true statement, right? We can choose any number greater than 1. 2 is greater than 1. So 2 times 2 is greater than 2. Is that a true statement? Yeah. 4 is greater than 2. Or let's try another one. For all x greater than 1. So that would be 5. So 5 is greater than 5. Well, that's true. 2 times 5 is 10 is greater than 5. So the upside down A is for all. Next, the backward E symbol means there exists. So this one is saying there exists an x such that x squared is less than x. Well, most people think that doesn't work. If I said 5 squared is not less than 5. 25 is not less than 5. So it could be a little tougher. Think of fractions. What if I said my x is a half? Well, what's 1/2 squared? Is that going to be greater than 1/2? Yeah, 1/4 is less than 1/2. And so any fraction squared will be less than the original fraction. And the next one is a such that. So 5 plus 2 is equal to 7, such that 2 plus 5 is equal to 7. We know this property as the commutative law of addition. So 5 plus 2 and 2 plus 5 mean the same thing, commutative law of addition.